Thank you, INQUA. Thank you, Dr. Benita and Dr. Bandana. I'm going to talk about what is happening today, what is happening now. Um, you know, and in seismology, you can do it in several ways. Either you can do it through monitoring earthquake, or you can use another proxy of plate tectonics, which is deformation. So you can monitor deformation and then try to understand what is happening today. What is the process behind earthquake occurrence? What is the process? How the process of plate tectonics is acting to produce earthquakes, and to understand the process, as well as to have some idea about how it's going to unfold in future. So with that, I'll start my talk, and I start my talk with the famous James Hutton principle, which says that present is the key to the past. So that's what geology is all about. But then what I'm interested, I try to extend it a little bit more, which is like this: the present allows us to understand the process. So if you monitor the earthquake or the processes, so it helps you in understanding the process. That's number one. And also it allows you to make prediction, and that's what, whether you use any pattern recognition, simulation, or in current, for example, AI ML, the whole idea is to use the past and present data, and make prediction for the future. That's how all our system, whether it's natural system or even in the economics, when it comes to finances, that's how all the systems they work. We try to use the past data and then try to make predictions so that it can help society. So and also at the same time, the way present is the key to the past, so it provides a peek into the past. Similarly, the present provides a peek into the future, and that's the whole idea of doing monitoring in current time. So all my talk is based on the monitoring of deformation, which we have done in last 15-20 years, assuming that these last 15-20 years they represent the current era, or at least the Holocene period. And then we assume that the process in terms of millions of years is not changing much, whether it's earthquake process or whether it's plate tectonic process, geodynamic process, not changing. It's kind of uniform, which is actually it is not. I mean, when you go into the process, all these processes are unfortunately very much nonlinear. But nevertheless, we assume that on that scale they are linear, and hence we try to understand using this short-term data. We try to understand the process which is happening over thousands of years or over millions of years, and then try to make the prediction. So what I do is, as I said, that I'm basically a tectonic geophysicist, another branch of seismology. That's another point that we are going more and more into specialization. So I don't call myself as a seismologist, but I call myself as a tectonic geophysicist who actually looks at deformation and to understand that the process, earthquake process, geodynamic process. So I use GPS, and we have a beautiful network of GPS in India. We have almost like 200 stations which belong to my parent organization, which is National Geophysical Research Institute, which I was responsible to establish. But then in total, we have almost like all over India, we have another 50-60 stations by other organization. But then Survey of India is coming up with very good network all over India by establishing almost like 1200 or 1300 GPS all over India. So I'm sure that in time to come, these data would be extremely valuable, and we will be able to understand the process much more clearly, much more robustly and reliably. Here, what I'm showing you is a GPS data using 1,600 GPS stations all over Indian subcontinent, and if you look at the southern part, I mean the part of India which is south of Himalaya and west of Indo-Burmese Arc. So these are almost like 65 stations which are within Indian Shield region. The problem with all these measurement is, or the constraint in all these measurement is that you need a long time series. What basically you are doing is you are monitoring the coordinate with time, and you are monitoring the coordinate with time with very high precision at millimeter level, and then you are looking at the variation of that coordinate with time. So you need at least 5 years data, 3 to 5 years data from the region where the deformation is very high, and even larger amount of data, maybe more than 6 or 7 years data from the regions where the deformation is very low. For example, the stable continental region of India, because you are looking at signal which could be as large as fraction of a millimeter. The internal deformation could be less than a millimeter per year, and that's what we are targeting. So for all this, what you need is a permanent station, and you need a longer time series. So I spend a lot of time on establishing this network, and then waiting from each project. I wait for 4 to 5 years at least to get something meaningful which I can use to understand the process. So as I said, we have a beautiful network in Himalayan region. So this is our part. So this is Garhwal Kumaon. We have almost like 30-40 stations here, Himachal and Jammu Kashmir. Then we have a beautiful network in Indo-Burmese Arc, including Shillong Plateau, which is here. And as Dr. Vandana Prasad mentioned, that there was an earthquake here on Sagaing Fault, somewhere here, just last month, or this month in fact, which caused a lot of damage in the region. There was another earthquake here, which we know as an earthquake which occurred just north of Mount Everest. These are two recent earthquakes, two earthquakes which have occurred in this year in Indian subcontinent. Okay, so what this slide shows, that India is moving at a rate of about 5 centimeter per year, and it's moving towards northeast. And as you see here, as you go in the Tibetan Plateau, these vectors, they start rotating a little bit. So that's what they tell you, that look, Tibetan Plateau is trying to escape towards east. That's what all of us we know. And then you enter into this region. This region we call as kind of Eurasian plate, but we prefer to call it as Sunda plate. So we have another beautiful network here in Andaman and Nicobar region, which is operational since last 20 years, and which has given us beautiful constraint on the deformation through earthquake cycle. We could estimate the co-seismic deformation. We could estimate the post-seismic deformation. Anyway, I'll not go into detail in Andaman Nicobar region in this talk. So all these sites, they're moving at a rate of about 5 centimeter per year. But if that was the case, then why do we have earthquakes here in the stable country region? So there must be some differential motion which must be going on in stable country region as well. And the best way to look at the deformation, internal deformation, and the convergence across the Himalayan region is to change the reference frame, that you you assume that as if India plate is fixed, and everything you are all these the motion, the plate motion, you are considering, as you are thinking as if Indian plate is fixed and everything is moving with respect to India. So these are called reference frame realization. And the whole idea is that when you want to understand the earthquake process here, then you're not interested as to how the Eurasian plate is moving or how the Indian plate is moving. What you are interested is what is the motion between India and Eurasia. That's all you are interested. So what I'm showing you here is assuming that Indian plate is fixed, and then I'm trying to look at how other plates are moving. So if you look at here, now you see that the Indian plate fixed does not mean that I have assumed that all these sides are showing motion as zero. Consider, remember that these are spherical plates, and there is something called Euler pole of rotation. So all these plates are rotating. So you try to remove that rotational component from the plate motion, and then you look at the residual motion. So now here is the residual motion here. Now this is a scale. This much is about 10 millimeter per year, and you see that all these sides they're not showing any motion here. There's hardly any motion here. And as you move towards north, you see a large motion here. As for example, here in the Indo-Gangetic plain, the motion is almost zero. But then as you move towards north, the motion starts increasing, right? And that's a signature that there's some convergence which is happening in the Himalayan region. And in fact, I'll come to that part a little bit later. So you also see that there are some sites, I'll show you in probably next slide. There are some sites here which are moving faster than the motion shown here in the deep south part of India. So there is some internal deformation which is going on within Indian plate, which is responsible for earthquakes in peninsular India. For example, we have earthquake cluster in Koyna-Wana region here. There was an earthquake here, which we know as Latur earthquake or Kilari earthquake, Jabalpur earthquake here, and the biggest earthquake here was Kachchh earthquake 2001, which we know as Kachchh or Bhuj earthquake here. So by looking at these data, we try to understand what is the process which is responsible for earthquake occurrence, and how stable is the Indian plate, and what are the other processes other than earthquakes which are taking place in the Indian plate region. There are several papers which people call that there is some segmentation of Indian plate between southern part and northern part. There are also we also have a lot of failed rift regions. For example, Narmada zone here, Godavari here, and then there's Aravalli, Delhi fold belt here. What is the role of all these paleo structures, or the failed rift or the paleo rift, in the deformation or in the earthquake occurrence process? So all these measurements, through these measurements, we're trying to understand the process happening at all these places. As I said, each study takes a lot of time to get some meaningful results. So the process, the entire subject and the entire data collection process is extremely slow, and it takes a lot of time to get some meaningful results. What you can do is, to better understand this, you can convert this into strain. So strain is nothing but the change in length upon length in a very crude manner. So what you do is, there are several means by which there are several measures of strain. For example, some people talk about second invariant, some people talk about shear strain, or deviatoric strain. So there are several measures which you can derive from these strain, but they all convey almost the same meaning. For example, if you look at here, so this is the maximum shear strain derived from in the Indian plate region, derived from these data. So you see that the maximum shear strain is here in the Himalayan region, of course. There's a lot of strain here, which is Indo-Burmese arc. So these are plate boundaries. The strain is of the order of almost like 100 nanostrain per year. And the strain here is very less, 1 to 2, or at the most going up to 10 or 20 nanostrain per year. Similar thing you can see in dilatation strain rate or in second invariant. But let's focus only on one estimate. For example, let's look at only the shear strain rate. Now, what you see here is that the map is kind of saturated with very large strain here, so you don't see much variation here. But but believe me that there's a lot of variation which is taking place here as well, and the evidence lies here. If you look at this region, the color is slightly different than the color here. So what I do is, let me remove this part to see what is happening here. So if I remove the Himalayan region and only look at the deformation which is taking place here, and then I look at the internal deformation, removing the rotational component of Indian plate, and if I look at only here, now mind you, this is the scale. This much is 2 millimeter per year. So there's hardly any movement here. Movement is less than 1 millimeter per year in the peninsular part of India. It's almost like insignificant, but it's kind of within the limit of error in the measurement. I'll show you. I'll give you an example of Koina, where we are almost touching the limit of the measurement of accuracy in GNSS or GPS measurement. Okay, what you see here in this part, just north of Narmada Son region, if you look at them very carefully, you see that the vectors are slightly larger. So there's more deformation in this part as compared to the deformation in this region. And if you convert it in terms of strain, then this is what you get. So this is a strain map. This is a shear strain map of the region. And what you see here is that the strain is extremely low here. Strain is almost like touching less than 1 nanostrain in this part of the region. But then in this region here, just west of Delhi-Aravalli fold belt and in the region of Kachchh rift, the strain is almost reaching almost like more than 2 nanostrain. So this has got strong implication that why do we have so many earthquakes in Kachchh region. Mind you, 2001 Kachchh earthquake was a very unexpected event. We are in a stable continental region. We are in of course, a failed rift region within the stable continental region, Kachchh rift. But nevertheless, that's part of that's part of stable continental region. So there was an earthquake in 1819, which we know as Allahabad earthquake. Now, a stable continental region producing a major earthquake in less than 200 years in the same region, that's very, very unlikely. So there must be something special about Kachchh rift, and in fact these data which the strain map which I'm showing you here is providing the clue. It tells you that look, the part here which I have a lot of our geologist friend, they call it Rajputana block, and I also prefer to call it as Rajputana block, that this block is moving slightly slower than the rest of Indian plate here, and the most of the motion is, mind you, that the network is not so strong as to define the exact boundaries, but nevertheless, Delhi-Aravalli fold belt here provides you a boundary in which just west of it, the plate is moving slower than the rest of the plate here. It's moving slower by 1 or 2 millimeter per year. So there must be there must be some motion taking place in Aravalli Delhi fold belt, but at the same time, the slower movement here must be exerting some compression on Kachchh failed lift region here, and that's the reason for Kachchh region to be so much productive. If I'll show you, I'll zoom this part here to show you what I'm trying to convey. So to understand this process in much more careful manner, what I'm doing is I'm choosing 3 distinct regions. A region in the north, for example, Garhwal Kumaon here, Himalayan arc. So what is the strain rate and how the process is taking place there, how the crustal deformation is taking place there. Then I'll pick up one region here in failed lift region here, which is Kachchh failed lift, how the deformation is taking place and what is the process which is taking place here. And then I'll pick up one region here, which is Koina-Varna, which is again a stable continent region. We all know that earthquakes in plate-bound regions are sort of easier to understand because we have some concept. We have concept of the strongest is the plate tectonics. Plate tectonics says that look, the deformation, that the plate interiors are sort of rigid, and deformation primarily takes place on the plate boundary. And what is the process through which deformation takes place? We say that it's basically the elastic rebound theory. So it says that look, the strain accumulates before the occurrence of earthquake, and then it gets released on the fault when earthquake occurs. So there is a process of strain accumulation and strain release in the plate bound region. But how does that process actually takes place in the plate interior region? That's still we sort of don't understand it in a very good manner. Intraplate earthquakes are much more complex, much more complicated than their good cousin in the plate bound region, where we do understand the earthquake processes, we do understand plate tectonics, how does it operate, how does it work. So that's what I'm going to do. So I'm going to show you 3 examples here: Himalayan convergent plate margin, and then failed lift region, and the stable continent region. Now these are the typically typed region of any plate margin, and I'm going to show you the deformation, how the deformation process, and how are the rates in these 3 different and distinct regions. So these are the 3 regions which I'm talking. Himalayan. This is Himalayan region. This is Kachchh failed lift, and this is Koina rift region. Koina stable continental region here. So this is again the map, the GPS map, GPS displacement rate or site deformation, site motion rate, and I zoom this part here, which is Garhwal Kumaon region. In fact, that's where I'm sitting right now. I'm sitting in Dehradun. So this region has, as you know, that this region has not produced a big earthquake, a great earthquake in the last 500 years. The last big earthquake, probably the big earthquake about 7 magnitude, was in 1803, which we know as Dev-Prayag Srinagar earthquake. There are some talks that there was 1505 earthquake which occurred somewhere north of Nepal, southern Tibet. Probably was a Himalayan earthquake, and probably that earthquake also influenced at least the Kumaon part. 1905 earthquake, Kangla earthquake, did not reach to Garhwal Kumaon. There was some talks that there were some reports in which there was some damage in the Dehradun region, but then it turns out that 1905 earthquake the rupture at least did not reach in Garhwal Kumaon region. So this region has not produced a big earthquake in last at least 500 or 700 years, to be safe on that side. And if I take a cross section here, then this is how it looked like. So this is Indian plate. So this is Indian plate here. It is under thrusting, and the whole thing, the whole drama is going on here. This we call as main Himalayan thrust, decollement, detachment, whatever you prefer to call it, and the motion here takes place in stick and slip manner. So so what happens is that during most of the time, this portion of the fault remains locked. It accumulates strain, and whenever the strain exceeds the strength of the rocks, the earthquake occurs. And when a big earthquake, great earthquake occurs, the entire main Himalayan thrust, right up to main frontal thrust, it slips. And the examples for this are like 1950 earthquake, 1950 Assam earthquake 8.6, 1934 Bihar Nepal earthquake, or even 1905. Of course, unfortunately, we don't have evidence of a surface break or the rupture reaching to surface in case of 1905. And then there are some sort of confusion as to whether 1934 earthquake also ruptured the main frontal thrust. It probably reached the main frontal thrust, but whether it actually ruptured and the surface part of it, and whether you can see it, there's a confusion in that part. 1950, there's some work from paleoseismologists which suggests that yes, it broke the surface. Nevertheless, so let me go to this region and show you what is happening now, how the deformation is taking place now. So that's the region, and these are the vectors of these are the GPS vectors, and this I'm showing with respect to Indian plate here. So this is Indian plate here, and as you move towards north, the velocity of these sites, for example, Gumkhalgir, Kotachami, Kotabag, as you move towards north, for example, go up to Badrinath, Oli, or Malari, the vector starts increasing. The length of the vector starts increasing. So it starts telling that, look, we know that Himalaya accommodates a convergence rate of about 2 centimeters per year. So as you move towards north, the vector will tend to reach to that mark of 2 centimeters per year. All these vectors are almost like 16 to 18 millimeters per year long. What you see here is that the lengthening of the vector is gradual. It's not suddenly. So here there's hardly any movement, and as you move towards north, the length of the vector starts increasing. So this is nothing but the elastic deformation. And if I draw as a profile here, and if I show you along a profile, so I'm showing with distance from MFT. So MFT is somewhere here, and if I plot all these vectors on this profile, then you see that all these sites are as if they're not moving at all with respect to Indian plate. There's very small movement, but as you move towards north, the site motion starts increasing. And believe me that if I assume that there is a main Himalayan thrust here, and if I do some simulation and I lock that main Himalayan thrust, I assume that this main Himalayan thrust is fully locked, then that's the curve which I get. This is the curve which I get. Now this is the curve which corresponds to strain accumulation. It considers that the main Himalayan thrust, which is supposed to accumulate all this, is currently locked and is accumulating strain. Now look at the beautiful match between the observation and the curve here. So this clearly gives you an idea that, look, the strain is accumulating in this part of the Himalayan region, and this strain is accumulating at a rate of about 18 millimeters per year in this part of the region. And as I said, now how much is the strain? What Holocene rate of deformation on main frontal thrust? They tell that, look, the Holocene rate of Himalayan convergence accommodated within the Himalaya is about 2 centimeters per year. It was about 18 millimeters per year. So what you imagine if there was no friction here on the main Himalayan thrust, then this is what you should have expected. That here the motion is zero, but then the moment you enter into the Himalaya, if I assume that this the long-term average, and assume that in another case assume that there is no friction, then the Himalaya should suddenly rise on the main frontal thrust. So this how the curve should have actually looked like. But the curve actually looks like this. So what does it mean? I'm sorry. It means that the point which is here should have, in long term, should move here. So it has not moved that much. So that much is the deficit in the movement. And it is this deficit which corresponds to the strain. And it is this strain which will be released, which gets, when it gets accumulated over time, it is this strain which will be released in the next big earthquake. And as you move towards north, the strain is decreasing. So earthquake will nucleate somewhere here. That's what all of us know. This is close to MCT region. Munsiari is here. So this is where the big earthquake will nucleate, and then rupture will propagate towards south, and all this deficit in movement which is taking place right now will be recovered during the next big earthquake. You can convert this into slip rate. For example, so what it says that, look here, all this, the MST is slipping at a rate of about 18 millimeter per year. That's what you expect. And here the MST is perfectly locked. The slip rate is almost zero here. So this is perfectly locked. And as you move towards this is PT2, by the way, and this is MCT. So somewhere close to PT2 and MCT you see that there is a transition. So MST here is perfectly locked. MST here is perfectly unlocked. It's slipping aseismically, and it is this part which is accumulating strain. You can convert it into locking, extent of locking, which is what is here. So this is perfectly locked. Red always denotes danger. So it's perfectly locked. So that's where this maximum strain accumulation is going on. And as you move towards north, the locking becomes imperfect. And here, by the time you are in Tethys Himalaya, beyond higher Himalaya, the MST is slipping aseismically. You can convert this into strain also, and the amount of strain which you get is of the order of about 70 nanostrain per year. Now remember this number. So in Himalayan region, you get strain of 70 nanostrain per year. And so what these measurements tell us? It tells us about how the process of deformation takes place, where the deformation takes place, how the process of strain accumulation and strain release takes place on main Himalayan thrust, and what are the typical strain rate here. So this is what this exercise tells us. And the strain accumulation is at the rate of about 17 millimeters per year, and shear strain is of the order of 70 nanostrain per year in this region. Now this is from plate bound region, Himalayan region. Let me go to the next one, which is which is failed rift region, paleo rift region, which is Kachchh region here. There's a beautiful network here by an institute called ISR, Institute of Seismological Research, which is based in Gandhinagar. And what these vectors, what their GPS measurements tell us, that look, again with respect to Indian plate, holding Indian plate fixed, look at it very carefully. So this is Kachchh mainland fault, and all the sides here they're moving towards north, and all the sides here they're moving towards south. So there's some compression which is going on here across the Kachchh mainland fault, and which is responsible for occurrence of these earthquakes. Now, this was, to me, we never expected this to see in our lifetime. We thought that the process is very slow, and it will be very difficult. We know that because these earthquakes are all strong, are all reverse, mechanisms. For example, 2001 Anjar earthquake here, or even the Allahabad earthquake here, they all convey that there's some compression going on. Now, to see it through observation was a surprise. And if I draw a cross section across it, that's how it looked like. So if I draw a cross section here, then what I see a differential movement here, and I see a systematic pattern. All these sides here, they're moving towards north, and all these sides here, they're moving towards south. And if I assume a compression across this rift, across this failed rift, on typically on which on the northern flank you have earthquakes like 1956 Anjar earthquake or Bhuj earthquake, and on the southern fringe or on the northern fringe, if you assume an earthquake like 1819 Alaband earthquake, and if I apply compression on it, then that's how the curve look like, and the curve fits these observations so beautifully that to me it was a surprise. And what it tells that, look, there is a compression of the order of about 4 millimeters per year across this failed rift. To us, it was a surprise again that how come a plate interior region, though of paleo rift kind, is experiencing such a large deformation. 4 millimeters per year is a very, very large deformation. But then, it also tells, this region also tells that, look, this region has been visited by an earthquake, a major earthquake in 1819, and then again, after 200 years, almost like 200 years in 2001, Kachchh earthquake. So this is also very unlikely of a plate interior region. How come? Where from you will get so much of strain energy, so as to be released by two major earthquake, which are only distant, which are only apart by less than 200 years. So there must be huge strain which must be accumulating in this region. And the recent observations, they say that, look, this part here further north is moving slightly slower, and if it is moving slightly slower than the Indian plate, the end result of it is applying compression on this Kachchh rift region. So that's where this 4 millimeter per year is appearing, because the Rajputana block is moving slower, causing earthquakes in Delhi-Aravalli fold belt and also in Kachchh failed rift region. I still do not know why we don't have a good history of a large magnitude earthquake in Delhi-Aravalli fold belt, but we do have good history of large earthquakes in Kachchh failed rift region. It is possible that there could be some a seismic motion, part of it could be going across Aravalli Delhi fold belt, so that's why that belt is not as productive as Kachchh failed rift region. If you look at the strain rate in this region, strain rate, mind you, the strain rate in Himalaya was about 70 nanostrain. The strain rate here is about 1 to 2 nanostrain. In fact, it's about 5 nanostrain in Kachchh failed rift region. If I show you the third typical stable continental region, which also has produced earthquake, then I come to Koyna region here. This is the last region which I'm going to talk. We have a network here, extremely good network in Koyna region, which is here. Earthquakes are considered or assumed to be triggered by Koyna region here, but that's only a triggering mechanism. What is it which pumps energy to cause these earthquakes? Triggering could be that, so these reservoirs could be contributing 1% or 10% of the strain energy at the most, but most of the energy should come from tectonic strain. So that's the reason because of which we put up a network here. So these are 5 stations within 25 kilometers. This is Koyna reservoir here. This is Wayna reservoir here, and all these earthquakes. These are all small magnitude earthquakes. And there was a strong magnitude earthquake here in 1967, which is considered to be reservoir triggered. But then again, the whole point is that what is it? Where from it gets the strain energy? Reservoir cannot provide that much of a strain energy to cause a big earthquake. A reservoir can only do a triggering mechanism, but it cannot cause an earthquake. So these are the earthquakes which are here, which are in Koyna region. So there's a fault. There's no visible surface fault in this region. So these are all inferred faults inferred from seismological data. So there's this fault here and there are two faults here. And these are the stations. These are the stations around Koinawana. The scale is this much is about 25 to 30 kilometer. So within 25 by 25 kilometer, we have 5 stations. And these are operating since 2013. So we have more than 10 years of data. And again, if you remove the Indian plate rotation from it, then this is what you get in terms of these black vectors. Now, even these black vectors, look at the scale here, this much is 1 millimeter per year. Even these black vectors, they are showing some residual motion, which is basically the unmodeled rotational motion in this region. So there is still some remnant plate motion in this region, which we need to get rid of. And then there are some ways, some tricks by which you can do. And if you believe me, then these red vectors are the vectors which represent the internal deformation of this region. And the rate and the deformation at the site is of the order of 0.2 millimeter per year. So as if now 0.2 is extremely small. It's almost at the limit of measurement in GNSS. Probably if I get a time series of 15 years or 20 years, probably I can still improve it. I can go up to 0.1 or 0.01 millimeter per year. But at this point of time, the deformation rate is about 0.2 millimeter per year. Now imagine, the surprising thing here is that look at the limit of deformation. Even the internal deformation of 0.2 millimeter per year is able to produce earthquakes in a region, right? So although these are all very small earthquakes, very small earthquakes, very tiny earthquakes, these are all, but then you do get, occasionally you get magnitude 4 and 5 earthquake in Koinawana region. So even such a small deformation rate of 0.2 millimeter per year can produce earthquake. To everybody, I mean, whether you compare it with New Madrid also talk about internal deformation of 0.2, 0.3 millimeter per year. So a surface deformation seen at the surface of 0.2 millimeter per year can also produce earthquake to anybody. That's a big surprise. You can do a lot of modeling. In fact, this paper came out just yesterday in BSSA, and you can put some faults and try to put slip rate on it to match the observation. And what it says that, look, a slip rate of almost like 1 millimeter per year or 2 millimeter per year can produce this deformation. So an internal deformation of 0.2 millimeter is responsible for producing these earthquakes here. The corresponding strain is less than 1 nanostrain here. It's almost like 0.1 to 0.5 nanostrain. So, you know, to put it in right perspective, nanostrain is 10 to the power minus 9. So we say that, look, if a region is going to produce an earthquake, and if earthquake occurs, the strain is of the order of 10 to the power minus 4. And in a convergent margin in subduction zone, the strain is about 100 nanostrain, 10 to the power minus 7. In a non plate bound region, within stable continental region, the strain could be in terms of nanostrain. So that's what Kachchh failed rift region says. But then it's a big surprise that a strain less than nanostrain, 1 nanostrain, almost like 0.1 or 0.2 nanostrain, can also produce earthquakes which continue to occur in Koina region in last 40-50 years. So there's it's kind of putting this as if there is no lower limit on strain accumulation, which can be responsible for earthquake occurrence. So that's to all of us, that's a big surprise that even such a low strain, fraction of nanostrain can also produce earthquake. And the good thing here is that you can sum up all these earthquakes in all these regions, and you can compare the geodetic strain with the earthquake release strain. So the geodetic moment rate, which is here in terms of nanostrain, is comparable to the seismic moment rate, and that's again a big solace, in the sense that that means these rates derived from GPS can be used to do to give some predictive models, because the two rates are quite comparable. So that's the summary. The Indian plate interiors has very low strain. The northern part is very stable. Northern part of the stable region is more deformable than the southern part. Southern part is certainly more rigid. Southern part includes Hyderabad, Bangalore, or Tamil Nadu, or south of or the southern part of Maharashtra. There is no segmentation. I mean, a lot of people talk about segmentation across Narmada zone. So there is no segmentation. The strain is very high in the Kachchh region and Himalayan region, obviously, because of plate-bound region. It deforms very fast at a rate of about 16 millimeter per year, and strain rate is about 50 to 100 nanostrain. And southern part, for example, Koina, it's almost on the lower limit of strain rate, 0.1 nanostrain. And of course, we need, just because we don't have good network across Godavari, or fortunately now we have across Godavari, or across Narmada zone, it doesn't mean that the strain rate is low there. Strain rate could be comparable to what we see in Kachchh, not as high as Kachchh, but then we need, to quantify that, we need more and more GPS measurements. And I'm hoping that because of Survey of India initiative of putting almost like 1,200 sites which are in operation, of course it will take 4-5 years to get some meaningful results out of it. We hope that we will be able to quantify the strain rate in much more robust and reliable manner for Indian plate region. Thank you very much.